So to begin with, I'm going to show you some of the equipment that we use in this lab. So right here, the first item, on the track we've got something called the Go motion sensor. And this thing basically works the way that a bat's sonar does, is that it puts out a sound wave, a little clicking noise you're going to be able to hear, and if there's some object in front of the sensor, that reflects the sound waves back towards the sensor, and the sensor could figure out how far away that object is. Furthermore, it can do it in real time, which means if the object is moving back and forth, it can measure how far away it is as it's moving, and then you can make a graph on your screen with a program I'm going to show you later that shows how far away it is. So you can make a position time graph of the object that's moving. And of course, if you can get a position time graph, you can also get a velocity time graph, which means you can get the acceleration of the object. So this sensor is a really good tool for studying kinematics. So to begin with in this experiment, what you're going to do is you're going to be pointing this at a partner, and they're going to walk away and towards the sensor, and you'll capture that motion as a graph on the screen. So there's a few things you need to be aware of with this sensor. The first one is that there's something called the dead zone, which is basically an area very close to the sensor where it can't accurately detect how far away the object is. The lab manual says that's 10 centimeters, but I actually find it's a little safer to use 15 centimeters as your dead zone. That just means whatever you want to measure, make sure it's at least 15 centimeters away from the sensor. And as long as it is, then the sensor can measure distances up to about 4 or 5 meters. Another thing to be aware of is that the sensor can be fooled by objects that are close to what it's measuring, so off to the sides. So when you're pointing this at your partner, do have them walk in the clear aisles between the desks, just to make sure that there isn't a desk or a chair that's going to confuse the sensor. Another thing to be aware of is that here on the front, there's a little window that flips up, and there's two settings for this. So there's the cart on the track setting, and then there's the person setting. So to begin with, you're going to want to switch this over to the person setting, and then you can flip this back. And as I said, you'll be pointing this at your partner. Walking away from the sensor is considered the positive direction as far as the computer program is concerned. So when your partner's walking away, that means their position's getting larger. So now I'm going to show you some motion using this cart on the track, just so that you can see how the computer program works in conjunction with this sensor. So this is the desktop of the lab computer, and all of the programs that we're going to use this semester are housed in this Physics 1100 folder. So you look around on the desktop and find this Physics 1100 folder, open that up, and inside you'll find a whole bunch of programs in there loose, and also a few folders for those weeks when we need to use more than one program. This week we're going to be using this velocity program down at the bottom. So double-click to open that up, and you get something that looks like this. So you've got a great big position time graph over here, and we've also got the data table for the actual data that gets graphed into the chart. Up here at the top we've got this little collect button. When you press that, that's when the sensor starts emitting its little noise, the little clicking noise, and it will start detecting how far away, in this case, the cart on the track is. So I'm going to show you this. I'm going to start with the cart roughly in the middle of the track. I'll press collect, and I'm going to move the cart towards the sensor and away from the sensor. So as the sensor got farther away, the position got larger. When the cart was getting close to the sensor, the position got smaller. So in real time, I'm able to see how far away that cart was. So now let me show you that dead zone I was telling you about. So if I press collect and wiggle the cart back and forth, you can see that, but if I come in close to the sensor and do the same thing, it just goes flatline. So when you're inside the dead zone, the sensor isn't capable of telling you how far away the cart is. So like I said, the lab manual says that the dead zone is 10 centimeters. I find it safer to assume it's about 15 centimeters. Now another thing you might need to do is you might want to adjust the size of your graph. So maybe the data is all squished at the bottom and you don't like that. So you can actually do it by hovering your mouse over top of the tick marks on the graph and just dragging it upward. However, I find that kind of slow sometimes, so there's a faster way. And that is you can click on the highest number and then type in a new value. So I'll type in 1, hit enter, and it resizes it so that the largest position on my graph is now 1. And you can do that to the top or the bottom numbers. You can click on it and adjust that value. So you can just click and drag, but I personally find it faster to just click on the highest number and type in a different value. Now if you've already watched that video on how to take screen captures, then you'll already have seen a little bit of this. So in the first question of the lab, they ask you to measure your partner walking away from the sensor at a constant fast speed. And then you'd capture that graph with the program and paste a screen capture of the graph here. Then you do it again for a constant slow speed and put your other graph here. Then, down here, you'd want to talk about the similarities and differences between those two graphs. Specifically, you'd want to talk about how you know which one was the fast walk versus the slow walk. Then, on the next page, they ask you to make a prediction for what you'll see if your partner was walking to the left toward the detector at a constant speed. What would that graph look like? So let's say that that's your prediction. So you draw it in, and then on the next page down, you're actually going to do that experiment. So your partner will walk towards the detector, and you'll capture that motion on the screen, and again, you'll screen capture your graph and paste it into your report here. And then you'd want to compare the experimental graph to your prediction. So you want to talk about the similarities and differences between what you measured and what you predicted. And to get full marks, you should talk about both the similarities and the differences. So the differences might be these bumps and wiggles and curvature that you see because your partner can't quite walk at exactly a constant speed. So those would be the differences. For the similarities, it's never enough to say that your two graphs look the same. You have to be specific. So I recommend you use graphing language. So you could say both graphs were linear, or both graphs were curved, and they both had a negative slope, or a positive slope, or a zero slope. You could say that they both had a y-intercept that started above zero, or at zero. One thing you don't need to talk about, however, is whether the slope of this graph looks as steep as the slope of this graph, because this prediction graph doesn't have any units, so in principle it can have any slope that we want it to. So don't talk about whether this graph and this graph look equally steep. That doesn't matter. Instead, talk about whether the graphs were both linear or curved, whether they had a negative slope, a positive slope, a zero slope, whether the y-intercept was above zero or at zero. So things like that. Use graphing language to talk about the similarities. So now we'll go back to the experimental apparatus, and we'll talk about what you do when you get to question 9. Now in step 9, things get a little more sophisticated. So for this one, you're going to be using the cart on the track, and for that reason, you need to grab your sensor and put it back on the cart setting. So cart on the track setting, and then you can put this on the end of your track with the window pointed down, the length of the track. It's best when the window is exactly vertical and maybe tilted ever so slightly forward. You'll get the best results that way. Before you start taking data, however, there's something you need to do, and you need to do it every time you're using this track, and that is that you need to level your track. So we've gotten new tracks since I made the original videos, and this is what the new ones look like. They've got 4 legs and a little table over here that your sensor sits on. And the bottoms of each of these legs is a screw that you can use to adjust the leveling of the track. So the first thing you should do is sort of poke at the track to make sure it's not rocking. So if the track is kind of rocking, then you may need to adjust just one of the screws to get it stable. Once it's stable, then you grab this level, and you're going to use this to level the track in 2 different directions. We're going to level it this way, side to side. We're also going to level it this way, lengthways, along the length of the track. But we're going to level it this way first, and what you do is you find the bubble that's going horizontal across the track, and just check whether the bubble is centered between the 2 lines. If it's not, then what you're going to do is you're going to grab the screws on the bottom of these legs, and you grab 2 at the same time, and you twist them in the same direction at the same time. And that allows you to level the track in this direction. So once you've got the bubble centered, then you also want to level the track in this direction. So don't leave the level lying flat like this. That's not actually accurate enough. You want to tilt it like this so that this bubble is at the top. And that's so that this metal surface here on the bottom is pressed against the metal of the track. So put it upright like this, and again, check whether the bubble is centered between the 2 lines. If it's not, then you'd want to go to one end of the track, and again, grab the screws on the bottoms of 2 of the legs and twist them at the same time in the same direction, until this bubble is centered. If, after you've leveled everything, you find that the track is still kind of wobbly, go ahead and ask your lab instructor to help you with this, but what the solution is that there is a second, smaller screw on each of these legs that actually screws upward until it locks against the metal of the track. So you can screw this second screw upward until it presses against the bottom of the track, and that will stop the wobbliness. You may need to do it on 1 or 2 different legs. But usually adjusting this second screw is not necessary. So only do that if you've leveled the track, but everything's still kind of wobbly. Do that pretty carefully every week that you use the track, because there are some experiments where you have a lot of trouble getting good agreement between your predicted value and your measured value if you haven't leveled your track well. Another thing to be careful of is to make sure that the area in the vicinity of the track is clear of objects. So for example, if somebody's got an elbow here, then the sensor may catch stray reflections from their arm, and you'll get a weird looking graph. Now, the motion that we want to capture here is a slow, exaggerated push and then a release. And you do want it to be a fairly slow push because when my finger is on here, it's accelerating the cart. And an acceleration on the graph should look like a curved line. And we want to be able to see the curvature. So we want a slow, exaggerated push so that we can actually see the curvature on the screen. So if it looks like your graph kinked up pretty sharply, that probably means you just flicked it too hard. So try again with a slow, exaggerated push. The other half of this is when I let go, so slow, exaggerated push, then release. When it's just rolling after my fingers left it, it's now got constant velocity. So we expect that to be a straight line on our position time graph. You want the velocity to be quick enough that you don't see much curvature due to friction. So on your graph, if the graph kind of curves downward, that's because friction was slowing down your cart. So you just want the velocity to be quick enough that you don't really notice that. So again, slow, exaggerated push, and then a release, and a fairly quick release. Now, before you actually capture your graph experimentally, you want to make predictions about what the graph is supposed to look like. So I'll give you just some mild hints here. Like I said, when my finger is on the cart pushing it, I'm accelerating it. That means that the graph should look curved. When I take my finger off, it's now rolling freely. That should be constant velocity, and the graph should then look straight. So talk with your partners and make a prediction about what you think your graph is going to look like. Then you'll do the experiment and compare what you actually got on the screen to what you predicted you would see. Now, if you've already watched that video on taking screen captures, then you've seen a little bit about what you do next with this. You're going to capture the graph of the motion on the screen, and then this week and this week only, we're going to make you do a hand-drawn graph of your data. So you'll screen capture just your data table, paste that into your report, and then you're going to make a hand-drawn graph and get an image of it using your webcam that's on the desk. And then that gets pasted into your report also. And then you're going to discuss things. So for example, you're going to calculate the slope of the rolling part of the motion, and you should be able to get a velocity of your cart from that. You're also going to talk about the differences between your predicted graph and your real-world graph off the screen. So for example, on the real-world graph, instead of it being a totally linear graph, you may have seen a little bit of curvature due to friction. So that was not in your prediction, but you may see it in the real-world case. So be on the lookout for that and talk about that if you see it. But you also want to discuss what's similar and what's different between your predicted graph and your measured graph.